Okay, so in the previous class, we have seen a bolted joint which is subjected to eccentric loading. Due to that eccentric loading, it is subjected to a shear stresses, that is primary and secondary shear stresses. Now, in today's class, we see a bolted joint again, but now it is subjected to eccentric load, but that eccentric load will create a direct shear stress and a bending moment. So, how we can do the analysis for the type of loading? So that we'll see now. So here I have a bracket. See here the load is not in the plane of the bracket here. Earlier thing it is in the plane of the bracket. If you see that numerical problems what we discussed, see okay this one are okay. If I take this figure, right. So here this is like something like this. So it is in the plane of the joint. So now it is perpendicular to the plane of the joint. So or you can say it is perpendicular, the load is perpendicular to the bolt axis. So here this is the bolt axis and this is the bolt axis. Load is perpendicular to this axis. So that's what we said, eccentric load perpendicular to the axis of the bolt. So if this kind of load is there, that means if the eccentric load is acting perpendicular to the axis of the bolt, so then how we can find the its effect, and also how we can do the analysis. So for that, let us a bracket which is fixed to a steel structure by means of 4 bolts. So here in this example also, it is denoted by our number of bolts are only 4 are considered. It is subjected to an eccentric force P at a distance E. So now here earlier thing is the analysis is completely different here. Earlier we defined the eccentricity is the perpendicular distance between the load line and the center of gravity. If you look at the previous case, yeah, if you take this one, so here we'll get the center of gravity. So we are taking this one as a eccentricity. So now it is not the case because the load is perpendicular to the axis of the bolt. So here the eccentricity is defined as from the plate, or maybe what he has said here is it is a steel structure. So it is from the steel structure, from this point to this point, load application will measure that one as a eccentricity as E. And also here, while doing the analysis, here we'll use different terminology. See now, if you take this is the, if I say this is the front view, this is going to be the, this is the front view, this is the side view. In the front view, you can see that the load is acting somewhere something like this. So this side you have 2 bolts and this side you have 2 bolts. So now, depending upon the effect of this force on this, we'll denote the bolts as, see you can see here, he has denoted 1, 1 here. So these 2 bolts are denoted as 1, 1 and these 2 bolts are denoted as 2, 2. Why? So now if you look at the side view and if you see the effect of this force P here. So because of this force P, what happened to this bracket? This bracket will try to tilt in this direction. So because you are fixed here, fixed by bolts here, you are applying a force here, so this force will tend to tilt the bracket something like this. So therefore this is the tilted view you can see here. The bolt is tilted something like this. So provided if the bolts are weak, if the bolts are strong enough, it will remain safe something like that only. If the bolts are weak here, so then it is going to be tilted like this. So that means here the amount of tilt, if this angle is theta, it is constant, so the top bolts are tilted more, or you can say the top bolts are elongated more. So this much, this is the delta. Delta 1 is the, see he has taken delta 1 is the elongation of this top bolt. So similarly here, so the point about which is it tilting, so the bottommost point where it is touching that steel structure. So this is the point of tilt here. So from the point of tilt, so here the deflection is 0. Then if you go upwards, obviously it is going to increase because it is rotating about this point or tilting about this point C. So now the elongation of bolts which are located at this location he has taken as 2. See here, you can see the center line. These two are on the same center line and these two are on the same center line. If you look at in the side view, so in the side view we have these two bolts are located only in this location and these two bolts are located only at this location. So that's why since these two, the top two bolts are subjected to same elongation, he denoted them as 1 only. And the bottom two bolts are subjected to the same elongation, so that's why he has denoted that one as 2, 2. But elongation of bolt 1, the set 1, I can say set 1 and set 2. So in the set here you have 2, sometimes you may have more than 2 also. So here these two set, this set the elongation is different from the elongation of this set. Okay, so now we'll see how we can find what are the stresses induced in these bolts as well as top bolts. I can say top bolts and bottom bolts. So generally, in case of the eccentric load which is perpendicular to the axis. So here this is the bolt axis. You can see this bolt axis and this is the bolt axis. Here the load is perpendicular to this. So then in that case, what we'll do is we'll denote the bolts as a number of sets. So depending upon their position in the joint. So this is one set and this is the other set. So now for this, to do the analysis, first again two effects are there like in the previous case. Here also this force, if I transfer this force to here, the center where the joint, the bolt is and at the center head of this system here again. So then its effect is going to be a direct shear stress plus it will create a movement. That movement is going to be now, see here this is bolt axis. So if I take this is x axis and this is going to be the y axis, the load direction is y axis. So your load is acting in y axis and the offset distance, this E is also along x axis, your movement is about z axis. You are going to, this P into E will create a movement about z axis. The z axis is not the longitudinal axis. So this is the longitudinal axis of the bolt. So longitudinal axis is nothing but along the axis of the bolt. So therefore, this moment will create a bending moment. So you can clearly see that also because of the bending moment only, it is tilting something like this. So therefore, the two effects are, one is direct shear stress, another one is a bending stress. So now you have to compute what is the magnitude of the shear stress and what is the magnitude of the bending stress. Then using any one of your failure theory, static failure theories, that is either maximum shear stress theory or maximum principal stress theory, we'll try to compute what is the maximum principal stress or what is the maximum shear stress based on the given data. Suppose for this bracket or for this bolts, if he has given the allowable shear stress, then we have to use maximum shear stress theory to compute what is the maximum shear stress in the bolts. Or in the problem, if he has given the allowable tensile stress, so then you have to compute what is the maximum principal stress. So using formula for maximum principal stress, you need to use bending stress as well as shear stress, you need to compute that. So based on that, you can easily evaluate the diameter of the bolts required for the given application. So that we'll see now step by step. The force P is perpendicular to the axis of each bolt. So here the P is perpendicular to the axis of the bolt. The lower two bolts are denoted by 2, while the upper two bolts are denoted by 1. That's what I said. So this is one set and this is another set. So this set is denoted by 2 and this set is denoted by 1. So how many number of bolts? Let us say sometimes there may be 3 bolts on the top and 3 bolts on the bottom also. We'll take all the 3 as one set on the top, all the 3 as on the bottom as one set. Then in this analysis, so again like in the previous case also we made some assumptions, that is the bolts are having uniform diameter and the secondary shear force is proportional to the distance from the bolt center to the center of gravity. Like that we made the assumptions in the previous case. Here also we'll make some assumptions. That assumption one is, here the bracket and steel structures are rigid. So that means here this is the bracket and this is the structure. So they are not going to deform. So then only it is possible. If they are also flexible member, then this delta will consist of combination of deflection of this bracket as well as bolt. So I don't know how to calculate what is the load taken by the bolt in that case. So that's why what you do is we'll assume that bracket and steel structures are rigid. That means there won't be any deformation in the bracket as well as the steel structure. Then the bolts are fitted in the reamed and grounded holes. The bolts are fitted in reamed and grounded holes. So here whatever may be the connection we are making here, so there is some preparation for that. So the bolts are fitted are reamed and grounded holes. So the holes are prepared using this process. So the advantage why we are using this assumption is to neglect the stress concentration. So we'll use this effect. So when bolts are and bolt holes are reamed and grounded, so you can ignore the stress concentration. The bolts are not preloaded and there are no tensile stresses due to initial tightening. So this is also one more assumption. We will assume that these bolts are not preloaded. So there is no preload on the bolts except this load. So before applying this load, there won't be any preload on these bolts. So with that assumption, we can take that this is going to be, it is not going to create any tensile stresses because of that one. The stress concentration in the threads is neglected. So like already tell, so with this assumption, you can neglect the stress concentration. So then last assumption is all bolts are identical. Last one is all bolts are identical in the sense all the bolts will have same diameter. So that we already, that kind of assumption we already made in the previous case also. Here also the same assumption. Then now we'll see the force P results in direct shear force on the bolts. So like already told, if I transfer that one to the center of gravity of this bolt system, but here no need to calculate the center of gravity. But only thing is just we'll measure that if I transfer from this location to this location, then there is a direct shear stress on the bolts and also that is direct shear force. Then you have a bending moment. So since the bolts are identical, the shear force on each bolt is given by P1 dash is equal to P2 dash is equal to P by number of bolts. So that means the direct shear force is same in all the bolts. Like in the previous case, previous type of loading, here also the direct shear load is same in all the bolts. So that is equal to the total load divided by, here you need to consider number of bolts, not number of sets of bolts. See here, I said 1, 1 and 2, 2. So that means don't take here only number of bolts as 2. You have to take number of bolts as 4. Instead of 2 sets, you have to consider what are the total number of bolts. So that means the number of bolts in each set multiplied by number of sets. So here you have to consider 4, not 2. So with that I'll get the direct shear force. Then once I get the direct shear force, then I can calculate what is the moment also. So moment is nothing but this P into E is going to be the moment. So that moment will give a bending stress. It will induce a bending stress in these bolts. So now as shown, each bolt is, so because of this bending, the bracket will tilt like this, because we assume that the bracket is a rigid. If we apply a moment to this, it will tilt like this. Because of that, the bolts, top bolts will be elongated by delta 1 and bottom bolts will be elongated by delta 2. So each bolt is stretched by an amount delta which is proportional to its vertical distance from point C. So now you can clearly see that from the diagram here. See, this is the L2 is the distance from the point of tilt. This C will call it as tilting point or point of tilt. So now the bolt center line is here. So then the distance between the point C to bolt center line of second set, we'll call it as L2. So then similarly point C2 from the distance from point C, that is the point of tilt, to the center line of the first set of bolts, that is L1. So now if this length is more, this elongation is more. From the diagram also you can clearly see that. So here only the delta 2 is only this much, very small quantity when compared to delta 1. Delta 1 is large. That is because of L1 is more than L2. So that's what here the condition. Each bolt is stretched by an amount delta which is proportional to its vertical distance from point C. So from point C, if the distance increases, so its delta is also more. So and also we know delta is nothing but the elongation. We'll assume that these bolts are made of linear elastic material. So we can easily calculate what is the stress in that also. So for that, Our delta, first condition here it is delta is proportional to L. That means delta 1 is proportional to L1 or delta 2 is proportional to L2 and so on. Then also we know that this delta is proportional to the force. Why delta is proportional to force? We know delta is nothing but elongation formula. Delta L is equal to PL by AE. PL by AE. So where P is the applied force, L is the length of the bolt, and AE. A is the cross-section area, E is Young's modulus. For a given bolt, L, A, E. If I keep these as constant, if I increase the P, delta L will increase. So that's why your delta is proportional to the force. And also this force is proportional to the stress. That also we know. Stress is nothing but sigma is P by A. Sigma is equal to P by A. So if you increase P, sigma will increase. If you decrease P, sigma will decrease. So that means your stress is proportional to force or force is proportional to stress. Likewise. Then we can correlate this delta to this stress value, or the stress is proportional to strain also. From your Hooke's law, stress is directly proportional to the strain. So now what we'll do is we'll relate these deltas to these force values. That is the thing what we need to do. By taking all these conditions, we can relate delta to the force values. So similarly, delta strain is directly proportional to the stretch. Stretch is nothing but delta L. So strain is delta L by L. So epsilon is equal to delta L by L. If delta L increases, epsilon increases. Delta L decreases, epsilon decreases. So that's why your strain is proportional to the stretch also. So then from all these conditions, what you can say that therefore it can be concluded that the resisting force induced in any bolt due to tendency of the bracket to tilt under the moment is proportional to its distance from the tilting edge. So that you can say that. So that means here we are from all these relations, what we can conclude here is, see, stretch is proportional to strain, strain is proportional to stress, stress is proportional to force. So that means, so in between, if I remove these two, from these two I can write force is proportional to strain, and from these two I can write force is proportional to stretch. So that means your F is proportional to your delta. That's what we need to conclude. So here we said delta is proportional to L1. So that means your F is, from that condition what you can do is F is proportional to L. Finally, you can arrive this relation, your F is proportional to L. Okay, so that's what we can conclude from this statement. Therefore, it can be concluded that the resisting force induced by any bolt due to tendency of the bracket to tilt under the moment is proportional to its distance. Distance we are measuring in terms of L. So from the tilting edge. So if I assume like that, then again the same relation P1 double dash. So the force which is due to this bending moment, the force in the first set of bolts will take it as P1 double dash, which is given by C1L1. So where C is the proportionality constant, and P2 double dash will get it as C into L2. So now then if you write the equilibrium equation, P into E is going to the moment. So one force is acting here, that is P1 double dash. Then the other force is acting here, that is P2 double dash. So then the moment, if you take moments about this point C, then P into E, that is going to be the moment due to the applied load. So here this is point C. So this distance we are taking it as E. P into E is going to be the moment. It should be equal to, so this load P2 double dash multiplied by this distance L2. So P2 double dash into L2. Why I have to use 2 here? Because in the given set I have 2 bolts, so I need to use 2 here. Similarly, the moment of this P1 double dash is nothing but this force multiplied by the perpendicular distance is L1. So that is P1 double dash into L. Since in the set I have 2 bolts here also, I need to use 2 here. So therefore, these are our equilibrium equations. So from this, if you substitute P1 double dash is C1L1, P2 double dash is C2L2 into this, from that you can calculate what is C. Once you know the C value, you can calculate P1 double dash and P2 double dash also. So from that, you will get C is nothing but your P by E into 2 into L1 square plus L2 square. If you substitute for P1 double dash is C1 L1. So it will become 2 into C into L1 square plus 2 into C into L2 square. If you simplify that, you will get an expression for C. So from that you can write expression for P1 double dash, and also you can write an expression for P2 double dash. That means in these two boards you have a same tensile stress. In these two boards you have a same tensile stress. So because that their elongations are same here, this is delta 1. For these two boards, the elongation is delta 1 top boards. For the bottom boards, it is only delta 2. So then the boards denoted by 1 are subjected to maximum force. So here you can clearly see that your P1 double dash is going to be more, because this length L1 is more when compared to L2. If you compare these two equations now, if you compare this P1 double dash and P2 double dash, so this part of the equation is same for both the things. Here in this also you have P by 2L1 square plus L2 square. This is there. Then this quantity is multiplied by L1. That is nothing but your C. CL1, CL2. So now, since C is same for both, if L1 is more than L2, then obviously your P1 double dash is going to be P2 double dash. So that's why here your L1 is more than L2. So that's why we written it as the bolts denoted by 1 are subjected to the maximum force, because L1 is more when compared to L2. So in general, the bolt which is located at the farthest distance from the tilting edge is subjected to maximum force. So we can generalize that one, the statement also. That means whatever may be the bolt which is farthest from this tilting point. So this is the tilting point which is away from this tilting point, or which is far away from this tilting point, then that bolt is subjected to the maximum force. Here in this case, this is bolt set 1 is the far away from this tilting point, therefore your P1 double dash is going to be the maximum. So now once you have P1 double dash and P1 dash, so we'll get the two stresses. That is, previous equations gives you shear and tensile forces. One is shear force, that is direct shear force. The other one is tensile force due to that bending moment. So these two are acting on this is the effect of your eccentric load. So then you can compute what is the shear stress and what is the bending stress or tensile stress also. Tensile stress, that is because of bending moment only. So therefore the direct shear stress is given by your P1 dash by A, where again this A is here 5 by 4 into DC square, where DC is the core diameter of the bolt. So this is the direct shear stress. Similarly, the tensile stress is nothing but P1 double dash by A. Again, this A is same formula, 5 by 4 into dt square. So now I have one shear stress, one normal stress. This is a tensile stress, this is a shear stress. So normal stress and shear stress, then I'll use the failure theories to find out the maximum, either maximum shear stress or maximum principal stress, where A is the cross-section area of the bolt at the minor or core diameter. So you need to use this formula. The bolts can be designed on the basis of principal stress theory or principal shear stress theory. Like I already told to you, so the bolt can be designed either based on maximum principal stress theory or maximum shear stress theory. So then, if I want to use principal stress theory, then we need to compute sigma 1. That sigma 1 is given by this relation. So you have a tensile stress, and you have a shear stress. So we know the formula for sigma 1, that is sigma t by 2 plus square root of sigma t by 2 whole square plus tau square. If I use this formula, I'll get the maximum tensile stress. Then for failure criteria or for design criteria, what I have to do is, I need to equate this one to your SYT, that is yield strength in shear divided by factor of safety. Yield strength in shear, yield strength in tension divided by factor of safety. This will give you the allowable stress, sigma allowable. So using this, you can calculate the diameter of the bolt. If you want to use maximum principal stress theory. But if I want to use maximum shear stress theory, for that first I need to calculate what is the maximum shear stress. Tau max is nothing but this is the expression for the tau max. Square root of sigma t by 2 whole square plus tau square. So then from this, so I can calculate the using. So from this I'll get tau max. Then for the design criteria, you need to take your tau max is nothing but SYS, yield strength in shear divided by factor of safety. So this we will call it as allowable shear stress, tau allowable. So Using this relation also, you can either this relation or this relation. Based on the data available to you, you can use any one of these two data, two relations, and you can design the bolt system. But in most of the cases, we'll assume that bolt material is ductile. You have to use this maximum shear stress theory when compared to this principal stress theory, because this principal stress theory will give you the better results for brittle materials, not for the ductile materials. So we'll assume the bolt material is a ductile material. So most of the cases we need to use this theory. That means this theory is recommended. So for the bolted joint, so you have to use this formula to determine the diameter of the bolts. So this is how you can analyze it. So using the following relationship, the cross-sectional area of the bolts and their size can be determined. So like already told, sigma 1 is nothing but SYD by Fs, or tau max is SYS by Fs. So the bolt material is usually ductile, therefore it is appropriate to use maximum shear stress area of failure. So that also already told to you. Okay, so this is how you can do the analysis when the eccentric load is perpendicular to the bolt axis. So now we'll take up one more numerical problem on this also, and we'll try to close this also. So before going to discuss the solution for this problem, so I'll give some time to you. Just you note it down. 2 minutes. Within 2 minutes, you note it down. Then so that we can proceed for the solution. Okay. So now we note it down. Once it is done, just inform me.
Sir, completed, sir.
Is it done?
Yes, sir.
Okay, right. So, okay, so we'll see now the solution. A bracket is fashioned to the steel structure by means of 6 identical bolts as shown in the figure. Assuming the following data, L1 is 300 mm, L2 is 200 mm, L3 is 100 mm, and L is 250 mm. P is equal to 50 kilonewtons. Determine the size of the bolts if the maximum permissible tensile stress in any bolt is limited to 100 Newton per mm square. So for that one, he has given two conditions. One is considering the shear stress, and the second one is neglecting the shear stress. So that means, so previously we discussed the analysis. So how we can analyze a bolt when it is subjected to an eccentric load which is perpendicular to the axis of the bolt. So we know that there is a direct shear stress and there is a tensile stress. So in the question, what he mentioned is, if you ignore the tensile shear stress, what is the size of the bolt? If you include that shear stress also, what is the size of the bolt? So because here the bending, the tensile stress value is going to be very large when compared to the shear stress, you can ignore the shear stress. That's why he has given two problems here. So anyway, we'll see that if you consider the shear stress, what is the value of diameter? If you ignore the shear stress, what is the size of the bolt? So that we'll see now. So here it is going to be a simple one only. So we'll see now. So now here three sets are there. So these two centralized for these two bolts is same. Center line of these two bolts are same, and center line of these two bolts are same. So therefore we have three sets. In each set again there are two bolts. This is set 1, set 2, set 3. So that's why he denoted it here itself 1, 1, 2, 2, 3, 3. So and the distance is L1, L2, L3. So he has given L1, L2, L3 values also. And L is nothing but here the eccentricity. E value is given as 250 mm. So now what you have to do is, first you have to calculate what is the direct shear stress, first direct shear load, from that direct shear stress, then what is the tensile load on each bolt. Then see here, this is your tilting point of tilt is C here. Obviously this is this set 1 is subjected to the maximum tensile force. No need to compute the force in these two sets also, only you compute what is the size of the what is the magnitude of stress load in the tensile load in the set 1. So then from that you can calculate shear stress and bending stress and tensile stress. Use your maximum principal stress theory to compute the sigma 1, then equate that one to your permissible tensile stress, that is 100. From that you will get the diameter. Okay, so okay, all right, so you can clearly see that. So if it is in tilted position, this is the free body diagram. You can see that delta 1 is more when compared to delta 2 and delta 3. So therefore here this first set of bolts will subjected to maximum tensile load. From this you can understand that point. Okay, right. So now direct shear stress given load is P. Direct shear stress is nothing but P by number of bolts. So here you have a total number of bolts are 6. Load is 50 kilonewtons. 50,000 divided by 6, which comes out as 8,333 is going to be the load on direct shear load on each bolt. So this is going to be the direct shear load. So then the direct shear stress is nothing but load divided by area. So P1 dash by A. So we'll keep A as A itself. Later finally we'll find out what is the DC value. Then similarly maximum tensile stress, the formula is this one. P1 double dash is P into E into L1 by 2 into L1 square plus L2 square plus L3 square. So here you have to calculate L1, L2, L3. So why you have to calculate L1, L2, L3? You have three sets. So earlier while discussing the theoretical concept, we consider only L1 square or L2 square. There you have two sets only. Now here you have three sets. You have to take like this. So then if you substitute the given data, he has given all these data L1, L2, L3, substitute it, we get P1 dash is 13,392.75 newtons. Then our sigma T is P1 dash by A. So P1 dash is this one. So that is 13,392.75. So then once you got all those values, then this is the formula to compute that one. So P1 sigma 1 is nothing but your sigma T by 2 plus square root of sigma T by 2 whole square plus tau square. So we calculated sigma T and tau values. If you substitute that again, this is going to be the your sigma 1. So now we need to equate the sigma 1 to the allowable tensile stress, that is 100. So from that you will get area as 173.86 mm square. So now you can refer your data book. One way of doing that is refer your data book. So from the data book, what you can do is you need to look at what is the area, this area. So then from that you can easily identify that for M18 the area is more than 173 or it is close to 173. So open your data book in that chapter number 8. You can see that also. So what is the area of each bolts? So for a given diameter M18, how I selected M18? If I take the table number 8.7, so first column is basic diameter or nominal diameter and last column is tensile stress area. So here we calculated that tensile stress area is 173.86. So now if I go for M16, so the tensile stress area is going to be 157 only, but here we required 173. So then if I choose 18, M18, that is a bolt having a nominal diameter of 18 mm, your tensile stress area is going to be 192. So therefore, it is going to be the diameter of the bolt what we need to choose. So that means we need to choose M18 bolt to find which is the suitable for the given application. So that this is the problem if you ignore the shear stress. If you consider the shear stress, that is the first part. Then second part, if you ignore the shear part, then it is somewhat simple. Only thing is you have to take sigma t and you need to equate sigma t to your sigma 1. If you do that, we get 133.93 mm square. Area is going to be 133.93 mm square. So then for that M16 bolt is sufficient. So that means, so for 173.88 you have to choose M18. For 133.93 you have to choose only M16 bolt. Right? So this is how you can solve the problem. Okay? So okay, later we'll see that next one. So here, so this is how you can solve the problem. So just you try to do the calculations and then you upload that. So note it, anyway, you note it down, this one I think. So if you have any doubt, then you can ask it. Otherwise, you try to finish these calculations and then upload the solution in the classroom. హలో హలో క్లాస్ ఏం లేదు సార్ ఉంది క్లాస్లోనే ఉంది 5 minutes ప్రాబ్లం చేసా నోట్ చేయండి అని చెప్పి ఆపా.
Sir, noted, sir.
Is done?
Note చేశాను సార్.
Okay. So if it is completed now, just upload in the classroom and then you can leave.
Okay, sir.
So I'm also closing the class.